Have you ever stopped to think about the invisible force that literally sculpts our entire universe? It's the silent architect that pulls galaxies together, that lights up the stars, and that keeps every planet locked in a perfect cosmic dance. Yeah, today we're talking all about gravitation. And it all starts with a question that sounds almost childishly simple, right? What keeps our feet planted firmly on the ground, and at the same time, it keeps the moon hanging up there in the sky? It turns out it's the exact same force. And figuring that out, well, that was one of the greatest scientific detective stories of all time. For thousands of years, we looked up at the stars and planets, and their movements were a total mystery. Cracking this cosmic code wasn't the work of one single genius having a eureka moment. No, this was a puzzle solved over generations, with each thinker adding a crucial piece to the board. I mean, just look at how this played out. It's like a scientific relay race. First, you have Copernicus, who completely flips our view of the universe, putting the sun at the center. Then Tycho Brahe comes along and spends decades making painstakingly precise measurements. He gathers all the raw data. Johannes Kepler takes that data and, like a master detective, finds the patterns, the what, of how planets move. But it was Isaac Newton who finally grabbed the baton and crossed the finish line, giving us the why. And Newton didn't just have a vague idea. He did something revolutionary. He described it using the fundamental language of the universe, mathematics. He boiled down this cosmic mystery into a single, beautiful, and elegant formula, the blueprint for attraction between any two objects in the cosmos. So here it is in all its glory. It sounds a little dense, but the core idea is simple. Every single thing with mass in the universe is pulling on every other thing. And the strength of that pull depends on two key things: how much stuff there is, their mass, and how far apart they are. So let's break those two down. First up, mass. This part is pretty intuitive. The more massive something is, the bigger its gravitational pull. The Earth has a much stronger pull than, say, a bowling ball. A star has a stronger pull than the Earth. More stuff equals more pull. It's really that straightforward. Now here's where it gets really interesting, the distance part. This isn't a simple one-to-one relationship. It follows what's called an inverse square law. Think about it like a flashlight. The farther the light travels, the more it spreads out and the dimmer it gets. Gravity works just like that. If you double the distance between two objects, the force of gravity doesn't get cut in half. It drops to just 1/4 of what it was. It weakens incredibly fast. So you might be wondering, if everything is pulling on everything else, why don't I feel the pull of a person walking past me? The secret is this number right here, the capital G, the universal gravitational constant. And look at it. It is tiny. I mean, mind-bogglingly small. This constant tells us that gravity is actually a super, super weak force. You need a colossal amount of mass, like a whole planet's worth, for that pull to become really noticeable. And that leads to one of the biggest paradoxes in physics. You see, there are 4 fundamental forces that run the universe. And out of all of them, gravity is the weakest by a long shot. It's unbelievably feeble compared to, say, the electromagnetic force. And yet, gravity is the force that shapes galaxies, holds solar systems together, and governs the cosmos. Why? Because while the other forces are powerful up close, over vast cosmic distances, gravity's reach is infinite, and it always wins. Okay, so let's bring this all back down from the stars and talk about how this grand universal law actually affects us in our everyday lives, right here on planet Earth. When we talk about gravity here on Earth, you'll often hear about little g. This isn't the force itself, but the effect of that force. It's the acceleration gravity causes. It's the reason things fall, and it's what gives you your weight. It's the tangible, measurable result of Earth's massive gravitational field. And on the surface of the Earth, that value is a pretty familiar number, 9.8 meters per second squared. All that means is for every second an object is falling, its speed increases by about 9.8 meters per second. Now, remember that inverse square law we talked about? Well, because gravity gets weaker with distance, that means your weight actually changes depending on your altitude. The farther you get from the center of the Earth, whether you're on top of a mountain or in an airplane, the weaker the pull and the less you weigh. Now, the difference is tiny, but it is absolutely real. So if gravity's pull is relentless, how does anything ever leave Earth? I mean, how do we send rockets to Mars? Well, you have to be going fast enough to hit something called escape velocity. It's the critical speed an object needs to just completely break free from a planet's gravitational grip and never fall back down.
And for our planet, that speed is just staggering. It's 11.2 kilometers per second. That's more than 40,000 kilometers an hour. If you're going any slower than that, gravity will eventually pull you back. But if you hit that speed, you're on a one-way trip to the stars. But what about all those things that don't fall back to Earth, but also don't escape it? They're in that perfect sweet spot we call orbit. This is that beautiful celestial ballet performed every second of every day by thousands of our satellites, all following the exact same rules.
And long before Newton, Kepler had already figured out the rules of this dance. First, orbits aren't perfect circles. They're actually ovals, or ellipses. Second, a satellite speeds up when it gets closer to Earth and slows down when it's farther away. And third, there's a perfect mathematical relationship between how big an orbit is and how long it takes to go around once. And the most beautiful part of all this? These cosmic rules, which we discovered by watching planets millions of miles away, apply perfectly to every single man-made satellite we've ever launched. From the International Space Station to the tiny GPS satellites that help you find a coffee shop, they are all obeying Kepler's laws. And because we understand these rules so well, we can engineer specific orbits for specific jobs. You want a satellite for TV broadcasts? Put it in a geostationary orbit way out at 36,000 kilometers, where it takes 24 hours to circle the Earth, so it seems to hang motionless in the sky. Need to map the entire planet or track weather? You use a polar satellite, much closer in, that zips around from pole to pole in about 100 minutes. Now, this brings us to a final, kind of mind-bending idea about what orbit really is. An astronaut on the space station isn't floating because there's no gravity. Oh no, there's plenty of gravity. They're, in fact, in a constant state of freefall. Imagine you could throw a baseball so incredibly fast that as it fell toward the ground, the Earth's surface curved away underneath it at the exact same rate. That's orbit. You are perpetually falling, but you're moving so fast sideways that you never ever hit the ground. So Newton's law was a triumph. It gave us the how. It let us calculate the force, predict the tides, and send probes to other planets. But it never really explained the why. Why does mass have this strange ability to pull on other mass across empty space? What is gravity at its deepest level? That question? Well, that would remain one of physics' deepest mysteries for another 2 centuries, setting the stage for an even more profound revolution in how we see the universe.